Hey there, my name's Kevin. In this video, I'll be evaluating the success criteria that I laid out in Criterion D using the design testing methods that you see on the right side of my screen that I created in Criterion D. My first criterion states that my algorithm is able to determine the most rational next move using the minimax algorithm. I'll evaluate this by showing my algorithm's decision-making process and test this by essentially playing against my AI on my game environment and seeing if other moves make sense beyond the code. So first, let's take a look at the code. Here, my AI essentially looks at every single blank space within the 3x3 grid, and it tries each possible position and calls minimax each time to see how the opponent will respond. After doing this, it copies the game state and asks minimax, what if I put an X here on any place on the grid? And after doing this, it can determine which place is the most rational move, which place actually minimizes your opponent's score and maximizes the AI's own score. So based on trying out each move, the AI returns information on its own move after trying out every single place on the grid. So that is essentially the code that determines the most rational move, the most rational next move, So on the actual game environment, we can see that, for example, my AI always blocks off any possibility for me to get 3 in a row. So by knowing this, I can also see visually that it's playing rationally. Determine when the game. My second criterion states that my algorithm is able to determine when the game is won, tied, or lost, so the win conditions. I can test this by finishing the game in a loss for myself or a tie against the AI. I can consider myself successful if my algorithm is able to detect that this has happened by displaying a message and ceasing to search for the next move. I'll also showcase the section of my code that demonstrates win conditions. Let's first take a look at the code. As seen here, these are all the win conditions, whether they be horizontals, so going across, or whether they be verticals, so these are all considered horizontals and verticals, so straight lines. And here, these are going to be the diagonals, so this diagonal and this diagonal. And you can see it displays all the different points in the grid in numerical format as a Cartesian plane, as a coordinate system. So I'll talk a bit more about that later when I'm evaluating, I think, the fourth criterion. So with that in mind, we can also test it out on the game environment. So essentially, my algorithm is able to detect whether or not all the previous moves in the game state essentially matches these winning conditions. And if they are, for example, then it displays that I've lost the game because the AI was able to connect 3 of their pieces in a row, and that matches with one of the win conditions here, and therefore I have lost this game. And the message also displays here. My third criterion is that my algorithm must determine the most rational next move for the opponent player. I will evaluate this by demonstrating the section of my code that determines the opponent's most rational moves. I created this criterion because it's only challenging for the opponent player if the algorithm is actually able to determine their next move in order to better suit their strategy. Here, the algorithm calls minimax every single time they try a piece on the board. So imagining this on the game environment, the AI will actually make a rational move by determining what my move will be next. So for example, if I place 2 in a row, the AI knows to block me off. How does it know this? It would try out placing a piece on every single one of the places on this board that are still available. And essentially what this does is that it calls minimax every time and sees what my next move is going to be. So for example, if it went here and checked that my move is indeed going to connect here and give me 3 in a row, then that means the AI is going to lose the game, it's going to match their losing conditions, and it's going to maximize my score, So essentially, because it knows that if it goes here, my next move is going to be trying to minimize the AI score and maximize my score, then it's not going to go here, because it allows me to essentially maximize my score while minimizing their score. The fourth criterion says that my algorithm must output the square of the most optimal move in numerical format as a coordinate. I'll evaluate this criterion by showing the output of my algorithm in coordinate form. I created this criterion because this is a notation that was easy for me to understand instead of just completely relying on ID tags. Moreover, if I were to pursue larger board games, this is very useful because they're commonly referred to the different squares on the board using coordinates. So as you can see here, these are all the win conditions that my algorithm can identify. So whether it's the diagonals or the horizontals, you all have it in coordinate form. As you can see here, my algorithm also returns the move of its choice in an XY coordinate, just like how the win conditions are structured in coordinate form. So because I've created code that outputs the most optimal move in numerical format as a coordinate, I believe I'm also successful in criterion 4. The fifth criterion is that I must create a 3x3 game environment. I'll evaluate this by demonstrating the section of my HTML and CSS. Before I do that, I created a 3x3 game environment for 2 reasons. First of all, I will need to use this skill in future projects, whether I'm creating a chessboard or a Go board. I need to create a game environment, so this is a good skill to learn now. But the second reason is because it allows me to test out the code that I have written as seen before. So here on the live server, you can see that this game environment is indeed here, and you see my HTML and CSS here. So this is also functional, as I will demonstrate in the sixth criterion later. My sixth criterion is to dynamically create the tic-tac-toe game environment using a function rather than hard coding it in HTML. I will evaluate this criterion by showing the code that renders the game environment into the DOM. I created this criterion, essentially, because, say, if I were to pursue a larger project to a feature that requires larger game boards, it would be very hard for me to adapt my project towards those things. So, for example, as you know, the Go board is 19 by 19, so with the code that I currently have, if it's only hard-coded, then I'll have to essentially code 19 by 19 grid inside my HTML file. That would be a lot of code. Instead of doing that, I created a function in my JavaScript file that essentially renders the game environment onto the HTML page. So this is the code right here. So this first function essentially creates 3 rows, and here this creates 3 columns. And for each of these columns, I basically added an image using the document.createElement tag. And essentially after doing this, I put the onClick class on all of the images. So all of the images essentially becomes buttons. So that is sort of how I created the tic-tac-toe document. And in order to actually adapt this to future projects, I can simply change this number right here to create larger board sizes. So because I was able to write code that dynamically creates the tic-tac-toe game environment, I can consider myself successful in Criterion 6 as well.